Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Dr. Phong Nguyen. Um, he will be giving a talk on deep operator learning for high fidelity flow field reconstruction from sparse sensor measurements. Phong Nguyen is an assistant professor at the Faculty of Mechanical Engineering and Mechatronics at Phenikaa University, Vietnam. Before joining Phenikaa University, he was a research faculty member at the School of Data Science, University of Virginia. His research focuses on physics-informed machine learning and reinforcement learning with applications in mechanical engineering and mechatronics. He has contributed to advancing these fields through numerous publications in top-tier journals and conferences, and his work bridges the gap between data-driven intelligence and engineering systems, aiming to develop innovative and efficient solutions for complex real-world problems. With that short introduction, the floor is yours, and you can start your presentation.
Thank you, Nas, for the introductions. It is my honor to be here presenting my research at Brown's Universities, and one of the Ivy League university in the U.S. For me, it was an honor because I spent like 3 years in University of Virginia doing actually physics info machine learnings. My advisor was Dr. Stephen Beck. He was still a faculty at the School of Data Science right now, and he's still chasing the route of physics informed machine learnings. And during my time at UVA, I was interacting with a lot of research from Brown's University, especially Dr. Kanakaris. He was actually one of the to be honest, from my point of view, the godfathers of physics for machine learnings, and I'm very happy to be here presenting and sharing the newest result on my research. So my research is about deep operator learning for regressive reconstructions of flow field. Like fluid flow, or it can be like airflow or any kind of flow field. From sparse sensor measurements. Before diving into my research, let me introduce about our university. So we are a university located in Hanoi, the capital city of Vietnam. So I believe most of you know about our country and our capital cities, but our university is a newly established one. We established in 2019. We are a very rapid developed one. We now, starting from 2019, now we have more than like 30,000 students. Our signature research was based off of autonomous vehicles and semiconductors trainings. So we are one of several that selected institution for by the Vietnamese government for training the students for the semiconductor industries. So that's a brief about us. And like the core power force of our university was lying on the research from the faculties and from the science that the faculties bring in. So that's why we're developing so fast and so rapid. So with that, let me start the presentation on my research today. So here's contents about my research. So first of all, let me introduce a little bit about the flow field reconstructions. What's the problem? And let me introduce a little bit about the ill-force inverse problem. Why flow field reconstruction from sparse sensor measurement is hard. And let me introduce next about the initial machine learning approach that we take, and then the key thing, the thing that we all love, the deep operator learning approach for flow field reconstructions, and can be finally finished with conclusion and some future works. So let me start by introducing what is the flow field reconstructions. So on the left, on my right side, as you can see, here is the description of the problem. So you are given a flow field, the one that I'm putting in here. Let me switch the pointers. So the one that you have in here, and usually you want to know about your examined flow field. So you're gonna put sort of like sensors over there to measure the quantities that you are interested into. So for example, in this case, we're interested in the velocity values of the flow, the fluid flow at that location. So we're gonna put several sensors in order to capture the velocity at that point at a given times. And then the sensors value will give you a series. Let's say you use a P sensors, then it will give you like P time series data. And at any given time t, you want to have a vectors yc, which is the measurements of your flow field. And the goal is that from this, you want to reconstruct the full original flow field. So then, mathematically, you can formulate it in this way. In a domain of interest, you're gonna be have a defined boundaries, which is in this case we have a rectangular one, and then an obstacles if you have, and then you have a set of sensors measurements, which is a place that you put your sensors on, and the goal is to reconstruct the original flow fluid flow from the sensor measurements. And the flow field can be anything, can be densities, can be velocity, can be thermal field, but in this case we want to focus on the velocity field. The applications of these technologies or research is very wide. The very common things you're going to see is for weather forecast, where you have sensors in various form. It can be a balloon sensors, like for example, like Google's, they send a lot of balloons on top, like they're sending them and then record the values of the wind velocities, and then eventually from those sensors they trying to reconstruct the flow field of the wind. Another application that you can think of is in aerospace dynamics, where you put, like for example, velocity sensors onto the like planes wings, for example. And then eventually what you want to do is you want to reconstruct the full original flow field in order to have a more information for example, like controlling the flight, or make it more stable. Another application you can think of similar to aerospace is underwater. So like for example, for unmanned underwater vehicles, for example, UUV, you can put sensors, like at the boundaries or at the boundaries of the UUV, and then you record the velocities of the flow of the waters, and then based off of that, you can reconstruct the water flow field around the UUV, and then based off of those information, you can eventually have a more optimal policy for controlling the UUV. The most things that you may see a lot is the in experimental fluid dynamics, where you put sensors at the domains of interest and then record their, like for example, velocities, and then eventually you can reconstruct the full state and the original flow field of the fluids. So that are some of the application of flow field reconstructions. But the flow field reconstruction from sparse sensor measurements, it is part of a bigger problem in engineering, which is state estimation from sensor observations. Like this problem is in fact a problem of state estimations, which is very common in engineering. So we have talked about, like reconstruct or, estimate the state of the fluid flow given a observation at several points, or, a fluid, the state of the system of the aerospace system given the observation at several typical points, like within the flow systems, and it's relatively similar to what we usually have in control theory, where, like for example, in robotics, you have a like LiDARs, a laser scan data, and then you need to estimate the position of the state of the robots, or, you are given vibration data, and then you need to estimate the state of the ball bearing. Although they are not similar in terms of their natures, but mathematically and, like from the control engineering point of views, they are really all the same problems. So why that problem is hard? So let's try to formulate the problem one by one, step by step, so that we see what is really the elephants in the room. So let's say you have a domain of applications, and then you have sensors at several locations. So the measurements of the full state or the original flow field usually is gonna be defined by a thing we call the measurement operators. We call it H. So the measurement operator, for example, in this case, we are measuring the velocities of the flow field, and we're using a linear operators. So, the values at a given time at a given values, we'll just keep that values. So that is a linear operator one. The operator that define the measurements values, which is called the measurement operators, and it will give the YC the vectors in the vector form, which is in the RP domain, which is a p dimensions space. Meanwhile, x is given vectors is given in Rn domain, and usually you're gonna just need a few sensors in order to observe the whole space, so that p is much smaller than p. P is much smaller than n, and because p is much smaller than n, H is likely ill conditions, and because of that, if you want to reconstruct the original flow field from the sensor measurements, which means that you want to find the inverse of H, because H is ill conditions, finding X as the inverse of H of Y is nearly impossible, even in the linear case. It's likely gonna be a one-to-many problems, and it's likely a ill condition problem, and it's really hard to solve. So how people deal with that, because it is very common, you usually have to estimate the state of the system out of your observations in control engineer, right? So how people do that? So traditional approach, people use sparse sparse optimizations. So typically what they will do is they try to solve an optimization problem where they try to minimize the observation real that you have, which is Y, and the observation that you apply by applying the measurement operator onto the reconstructed field, and then the problem will be solved with the reconstructed field as the variables, which is the x hat in this case. This problem is still very hard to solve because you know that x is within the space of Rn, which is a very high dimensional one. So because of that, people try to reduce the dimensions by using a method like proper orthogonal decomposition, for example. But still, that is have some limitation that we will see later in the result sections. Another approach that people may use is doing data assimilations. Usually what they're going to do is they're going to construct a dynamic model to predict the pseudo true state based off of history. And then they're going to use the sensor observation to correct the predictions. So the goal is to assimilate what you're going to see. And a more common approach, the final one in this day they're going to use because of the raise in terms of machine learning, is reverse shape reconstructions that usually people are going to use supervised learning to learn directly learn the inverse operator using data, and that will be our focus for the today's talk. So that is the ideas for our first initial action on FLRNet. That's what we call, which is a deep learning for flow field reconstructions. So our whole idea is that if you try to learn the direct map from the observational space, which we call the RP, to the state space, is going to be hard because the large differences in the dimensions. It causes unstable training because it's ill conditioned, as you know already. The lack of data in terms of scientific data may cause overfittings. And even if you try to reduce the dimensions of the state space by method like proper orthogonal decompositions, these linear-based method may not be expressive enough to represent the complexity of the flow field. So because of that, we come up with an idea of using autoencoder to learn the representations of the high-dimensional flow field. So what we did was that we construct a autoencoder, which is learn a latent representations, low dimensional representations of the original flow field. So as you can see in here, that Z is the latent variables is expressed by the term of an encoders. X is your state at the state space, and then the reconstruction of X from Z is done by a decoders. And after we were able to learn that latent space, what we need to do is just use deep learning to correlate from the sensor measurements at the observational space to the latent space, which is Z is the function of ZGs to the observations. And after we were able to correlate it to the latent space, we will use the decoder X DZ in here to reconstruct the state space. So that's the whole idea. So here is the architecture design based off of that. So first, we try to use an autoencoders. So in this case, we use variational convolution-based neural network for our encoders. So it will learn the latent representations of the flow field, and then try to decode the latent representations out of the latent space. So that is the first stage. And in the second stage, we try to correlate the sensor measurements onto that. So that is quite simple, but will be proved to be very effective. So we try to train with a classical flow around obstacle problem. So if you already know, it is a very classic problem in fluid dynamics. So like you are given a domain in this case, and then you have a obstacles, and then the fluid will flow through from the left, around the obstacles, creating these kind of patterns. So in this case, we test several sensor distribution strategies. So we test three type of sensor distributions: randoms one, the other one is rounding the obstacles, and the final one is sensors are distributed near the edge. And then we also test several numbers of sensors. In this case, we test 8 sensors, 16 one, and 32 one. So here is the result of our initial state. So as you can see, the first row is the ground truth from computational fluid dynamics analysis. So that's coming from the CFD one, and the second one is the one that we propose, the FLRNet. The third row is the direct one that we use neural net, the fully connected layers only to directly correlate from the sensor measurement to the two-state flow field. And the final one is the one that we try to use POD to represent the original flow field and then correlate the sensor measurement into that low dimensional representations. So as you can see that FLRNet, it can reconstruct the flow field the most accurate. We can actually see the MAV, the mean absolute error of the reconstructions, right below the reconstruction result. So as you can see, the values of the reconstruction, the error of the reconstruction is relatively low from the FLRNet compared to the other methods, which means that approaching using neural network is a good idea to go. Visually, the error is from the proposed method is good, but we didn't have any numbers to compare. So let's take a look on that. We further analyze the result by cutting the result into profile. So we cut the result into a vertical profile and then plot it, compare it from the result from our proposed method to other methods. So as you can see in here, our method is the solid line one is always lying at the lowest level, which means that we are approaching at the good directions. And we also test the error with respect to the time evolutions of the fluid flow as well. So for example, in this case, the fluid flow is divided into 40 steps, and we divide it into 40 time steps, and then we analyze the values of the errors and those time steps. And as you can see in here, the solid line is FLRNet using reciprocal loss, and the red line is the FLRNet using Fourier features. The Fourier feature is the one that we are proposing, the one that is consistently lying at the lowest level. So, and then one thing is very funny is that at first it seems like the error is kind of stable, and then it's kind of hit a peak at around step 20s, right? And then all of a sudden it's start gradually reduce it can be explained by the fact that, like you start having the flow getting into the domain and then, moving around the obstacles. And then all of a sudden, the instability triggers. And then, there is some instability in your flow. And then finally, after the instability trigger, your flow getting into the equilibrium state. So that is explaining why you have a, rather low error, which is very very stable, and then all of a sudden it start peaking and then, reducing again. So that can be explained because of the nature of the fluid flow phenomenon. We also test the effect of the sensor sensing. So in here, what we did was we test the number of the sensor used. So here we test 8 sensors, 16 sensors, and 32 sensors used. So as you can see, the performance of the method, the proposed method, the red line, that one is consistently the lowest one, which means that even when you check the sensors, our proposed method is still performing the best compared to other method like using linear dimensional reductions, or using the NLP, the nonlinearity fitting using neural net methods. We also test several layout of the sensors. So we test random layout, sensor distributing around the obstacles, and sensor distributing near the edge. And as you can see, very interesting is that sensors distributed randomly tend to give a better solutions, which is, as you can see in this case, why the sensors putting around the obstacles, it gives actually the worst performance. So you can think about this as, like, for example, in the case of sensors are randomly distributed, you can think of it, you can think about this as a, experimental fluid dynamics, where you try to put sensor within the domain. And for the case of sensor are distributed around the obstacles, you can think about the UAV or the aerospace dynamics examples, where you try to put the sensors around the wings of the airplanes to try to reconstruct the airflow around the airplane in order to optimize it. And then of course, if you put the sensors well distributed around the domain that you're trying to examine, it will likely to give you the best result. But all in all, although the performance of the case that sensor are distributed around the obstacles it's not the best, but it's still at the level that you can expect. And if you kind of notice is that the method that we're trying to proposing, the FLRNet, it's consistently the most accurate. And we also test the effect of the fluid system, meaning that the effect of the noise within the sensor measurement and the effect of the Reynolds numbers. So if you work in the domain of fluid dynamics, you may likely know that Reynolds number is the one that played the most important role in terms of determining the characteristic of the Reynolds of the flow. So either the flow is laminar or unstable flow, or turbulence flow. So in our case, we try to test the case where the Reynolds number is below 1000. So we try to stick with the laminar flow regions. So as you can see, the performance of our proposed method, the FLRNet, the one that use neural net and autoencoder for dimensional reductions, it's constant consistently the lowest one. And for the robustness with the noise, our method is also the best compared to other method. As you increase the level of the noise in here, so like in the sensor data, you try to inject some Gaussian noise within the sensor's values, and then you probably see that the reconstruction result of FLRNet is still the best. So for recapping, you may try to you may actually see that deep learning is a deep representation learning. The VAE is very efficient to learn the low-dimensional latent representations, which can be used to support the learning of the inverse operator, because obviously you try to reduce the dimensions, you try to reduce the differences in the dimensions between the observational space and the state space, so that the process of learning the inverse operator will be much easier. And VAE itself, with the noise and the stochasticity injected in the architecture is robust. It is likely to be very robust with the noise as for different sensor testing. But one major thing is that it is really mixed, and it is really the key of the talk today is it's only can operate on the fixed resolutions. So if you, for example, change the dimensions of the original fluid flow, for example, if you don't, for example, in that experiment, we use 128 by 256 pixel to represent the flow field, original flow field. But if we try to increase or reduce the resolutions, the method likely will be broken. So that is where we need some other solutions. And that is when we really start to think about deep operator learning, which is the start of the talk today. So because of the resolution dependent problem of method like CNN, we start thinking, I myself and my student, we start thinking about operator learning as our solution. So we take a step back and try to analyze the problem. So here's what we see. So let's take a look on our problem, right? Like you have an state space which represent your flow field, and you have the observational space which represent your sensor measurements. So what you want to do is, from several observations at several points, you want to reconstruct the flow field, which is basically a function of time, right? Because it's a dynamic process. So if you really think about this, then the sensor measurements at a discrete time point, right? It is really the observations, and the original flow field, which is a function of time, is really a target like target function that you want to map to. And the observation at a discrete time point, it is really the discrete observation of the source functions, right? And then you can really formulate it as a deep operator learning problem, where the target is to learn the inverse operators, which map from the observational space to the functions in the observational space to the function in the state space, and the functions in the observational space, which can be represented by the dot line in here. You can represent it as several discrete observation at several points, and from these observations you really want to learn the it is kind of a little bit counterintuitive, but people in control engineer call it the forward operators. So you really try to learn the forward operators, which really give you the original flow field given as a function of time, which is a continuous function. So that's where we see that where my group sees that it is really close to deep operator learnings, and then we start thinking about if we can use deep operator learning in order to solve this upcoming problem. And then that is where we see that we can really use DeepONet for solving the problem. So we can treat the source domain as the observational domain, and the target space is that state space, which is both of them are function of time. And from the original domain, you are trying to map from the observations at the original domain, which is the sensor observation, which is can represent by y tau 1, y tau 2, y up to y tau n. And tau 2 to tau n is really the nothing but just the time values at these particular points. And then from these sensor observations, we use Voronoi embeddings, which we will explain later, and then send it into a branch net. That part you already know. And then we try to predict several values, and at the same time at the target domain, which is really nothing but just the time domain, we have the time values of the target domain, and then we have tau 1 to tau n serving as a reference, nothing but just a reference for t to stay in. And based off of that, based off of this input, we use the DeepONet architectures in order to try to reconstruct the original flow field, which is the function of time. One special thing in here that you might be seeing is that so usually in the original, like in traditional DeepONet, you want to see it this part, the FNO in here, it is either CNN or MLP, which is rather not really any operators, but in here we use Fourier neural operators. The goal is that for DeepONet you can achieve the learning of the operator that map from function to function in time. But the reconstruction is not just the function of time, but it's also the function of space. It is also a function that defined on the spatial domain. So what we really want is we really want to achieve the reconstructions that is invariant with the discretization in both space and time. So that's why in here we use Fourier neural operators. For the details, you can actually refer to the original Fourier neural operators papers, so that you have a more ideas on what is going on in these layers. For the limit of this talk, I will not deep dive into this, but in this particular architecture, we use Fourier neural operators, and try to predict the same values of B from 1 to n, just like traditional DeepONet, which I believe you know very well about that. And then combined with the embeddings and the analysis from the target domain, and then combine it to make the final predictions, which is our original flow field defined as a function of time. One of the and here is just a explanations of the FNO layers, nothing special. One of the special thing about our thing is that we use the Voronoi embeddings for encoding the information from the sensor measurement. So if you recall, so let me try to explain a little bit in here. So in the flow field in here, you try to put several, sensors into your domain, and then you try to, for example, in this case, you try to record the velocities, and each of these sensors, with respect to time, will give you these values. And if you just send these values into our Dibyajyoti, it may not really work because there is no spatial awareness, and it will likely be overfit, just like with the FLRNet previously. So what we did was we used a thing they call the Voronoi tessellation. So in order to determine which area in the spatial domain affected by which sensor. So like, for example, you use a Voronoi tessellation to divide the space into area like that, and then each area is like divided based off of the sensor locations, and that sensors, for example, the sensors in here will affect the values of the sensors in here will affect all the pixels in the area that it was defined to be affected by the Voronoi tessellations. So by doing so, you actually have just convert the time series data or the vectors data into video or image data, which is much easier to handle by the Fourier new operators. So based on and then based on the input from the Voronoi tessellations, you send it to the FNO, and then basically FNO is naturally handle the 2D image input, and then process the output just like normal CNN, nothing special. So for training, we use instead of running our own simulation like the previous one, we try to use the CFD bench data. So the CFD bench data, they have a data set for fluid flow, around the obstacles. They have a domain of physical size of 0.14 meters by 0.24 meters, and it was divided into 140 by 240 pixels. There are 50 simulation cases in the data sets, and the velocity is varying from 0.1 to 5 millimeters per second. And for each of the simulations, we with the total durations of 1 second, we divide it into a 1,000 snapshot case, and then we use 32 sensors to measure the velocity, just like in the previous example. And here is the initial result of the reconstructions. So the first row, as you can see, is the ground truth from CFD provided by CFD bench. The second row is the FLRONet, which use Fourier neural operators as its branch net. And we have two other variants, which is the FLRONet using MLP and FLRONet using UNet, which is relatively similar, but just difference is that one is using the MLP instead of Fourier neural operators, the other one using UNet instead of Fourier neural operators. And then the final one we try to benchmark is the FNO3D, which is naturally from the claim by the Fourier neural operators authors that it can achieve super just zero shot super resolution in both space and time, which is quite remarkable. We're trying to compare ourselves to them. So as you can see visually, FLRONet for all three variants, visually it's provide much better reconstructions accuracy, visually compared to FNL 3Ds. But let's see the numbers. How does this say? So first of all, we test the average mean absolute error with respect to the with respect to different input velocity within the testing data. And as you can see, FLRONet is the one that we are proposing. It is a Dibyajyoti using FNO as its branch net for the reconstructions. The MAE is consistently the lowest. The other two variants also slightly, perform worse, but is much better compared to the FNO3s. So that is what we can see from seeing the average MAE. But we not only care about the accuracy, but we also care about the consistency, especially in the case of missing data and in the case of noise injected into the measurements. So in the first case, we try to test how the model perform when they are missing some sort of sensor measurements. For example, like if you are have a sensor that is malfunctions or you lost the connections and you lose the connection to those sensors. So what happens? So the blue one is the one that represent FLRNet, and interestingly, it's become the lowest for the FNO3Ds. It's very consistent actually. It's when you miss like 2/3 of your data, when you miss like 20 sensors, the performance is likely the same. But as you can see, if you use FNO as your branch net, the performance kind of like not really getting worse. But for if you use like UNet and NLPs, somehow the error is kind of like drastically increased as the missing the amount of missing data is increased. In the case of noise, in this case we add noise into the sensor observations, and as you can see, like we add from 0% to 10% of noise, and we add more noise. Our FLRONet, it tend to perform better compared to other method like FNO CD. So that's what we can see in here. We not only see we will not only validate the model based off of the graph, but also by seeing what is going on actually in the reconstructed field. For example, in here we add the noise up to 20% and see how the model perform, how the error perform onto the with respect to the ground truth. And as you can see, even when you add a lot of noise, the reconstructed field in the case of FLRONet is still very good. For the missing of sensors, thanks to the Voronoi tessellations, even when you miss like 2/3 of your sensors data, it still like persists very well. But I would not say that when you're missing like 20 sensors, I would not say these results are good, but I rather will come back to like you can miss like half of your sensor data, and then you still can reconstruct the very effective flow field, which means that you may just need those kind of data in order to accurately reconstruct your flow field. One of the things that I want to achieve the most beside the accuracy, when applying operator learning is the zero shot super resolution capability. So in here, what we want is that we want to be able to make a prediction regardless of the resolution in both spatial domain and temporal domain. So with the Fourier neural operator serving as our branch net, we were able to reconstruct the flow field, regardless of the resolution requirement. So, whatever the resolution required, the model can, can really, what is it like? The model really can get into all of this. The model can, give the solution for all of the case. Even like, for example, in this case, 1x is the original flow field, and then here is the zoom in view of a particular area. And as you can see, the model can perform a super resolution without retraining up to 8 times. And the reason for we not being able to going into 1632 times is because we don't have any GPU available for running those. We actually can go even more than that, but our computing facilities doesn't allow those. So that's why we stop at 8 times super resolution. And interestingly, the computation cost, although you might think that when it comes into high resolution prediction, it might increase like exponentially, but it's not really the case. Based off of what we analyze on the 2 GPU that commonly used for this particular problem, the Tesla V100 and A100. It seems that the computation cost, it just increase linearly with the operating resolutions, which means that if you actually can have a bigger GPU, for example, than the A100, you actually can achieve much higher resolution if you need it. The only limitation is your computing capability. So that is for the spatial domain. How about the temporal domain? The temporal domain is actually really the one that I'm trying to focus when I try to, conduct this kind of research. And interestingly, FLRNet can derive the reconstruction field any given time in between the observation time. What does it mean? Which means that so like let's take a look on this particular plot. You have the time in here, t at 0.175 and 0.18. They are the 2 moments that you observe the values of the sensors, right? And if you remember in the FLRNet, you cannot reconstruct the flow field at any given time in between that. But with the FLROnet, you actually can, because of the Dibyajyoti formulation. It's allow you to learn the mapping from functions to another function, which is in this case, the original flow field is a function of time, and which means that you can actually reconstruct the flow field at any given time in between the observation and time, right? So for example, in this case, you don't have the observation at the time t equal to like 0.177, but you still can be able to like reconstruct the flow field for that particular time. And how is it accurate? It is pretty actually accurate in this case. Like for example, in this case, I try to analyze a time window of 20 steps, where the observation is only given in a step 0, step 5, step 10, 15, and 20. and the model have to reconstruct the time at step 1, 2, 3, 4, and then 6, 7, 8, 9, anything in between these observations. And we do have the ground truth for that because of the CFD bench data. And then based off of the prediction and the ground truth, we try to record the MAE for those particular time step. And interestingly, the error is very consistent and reasonable compared to the error at the observation time, which is the red blocks in here. It is quite remarkable because you don't have the observation, which means that you don't have the informations at those intermediate time, but because of the inductive bias injected in the Dibyajyoti, you were able to reconstruct accurately the flow field at this particular time point, which is quite incredible from my point of view. And you may ask, like we just show at some certain level of resolution in time. What if you go even further, even finer, or even like come to infinity? Is it really a continuous time model? So then, based off of this, numerical evidence, I myself personally can, confidently say that we somewhat achieve a continuous time. So in this case, we try to refine the prediction at an even finer time step, at the finer time resolutions. So we try to go for like 10 e minus 8 and 10 e minus 1 e minus 7 second accuracy, and then we can actually go even further than 1 e minus 8. It can be 1 e minus 9, 10, 11, 12, whatever you name it. And the small size of the time step that can FLRNet can achieve is nothing but just the numerical error that your computing system had. So which means that basically you have no limit in terms of how you can refine the solution in between two observation time, which means that numerically you are achieving a continuous time model, which is quite a problem that I myself and my group at UVA was facing during my 3 years over there. So in short, we was able to test that the Dibyajyoti architecture can be used for flow field reconstructions, and it provides robust and consistent accuracy. More importantly, it provides zero-shot super resolution in both space and time. And the validations, however, although we have validated and then test all of those hypothesis, but validation on other type of problem is still needed. And that is also going to be our future work as well. In the future, in Vietnam, we are trying to apply this for air quality monitoring. So like air emissions, gas is a very big problem right now in Southeast Asia because of the development speed of the countries and the regions. Another things that we are trying to do is climate monitoring and forecast, where we're trying to monitor and forecast the tropical storm in the South China Sea regions. Another engineering application that I myself and our faculties here in the mechanical engineering department is trying to solve the problem of controlling UAV and then UUV. UAV is the flying one, and UUV is basically the diving one. So that is our plan within this particular kind of research. We hope that we can have some newer result that can be shared in the near futures, and if we have, we are happy to share with you all. For this, it will conclude my talk, and I will stop by now, and then ready for receive any kind of question that you have. Thank you.
Thank you so much for your great talk. Before asking other audience for question, we have a question here. What are the inputs to FLRNet, and what feature transforms are used, if any? What is the size of the network and the volume of training data? How does it perform if there is a little noise in the system, sensor measurement, model parameters, etc.?
Thank you for the question. To answer your question, for the FLRNet and the FLRONet as well, the input to the system is the sensor measurements. So let me try to address the problem once again, that within the domain we have put in the sensors, any kind of sensors that can measure your quantity of interest in here, and then each of these sensors will give you a time series data, just like in this one. So one is one axis is the time, and the other one is the values that we interested in. So in this case, we are interested in the velocity values at this particular point at a particular time. So based off of a number of sensors that we put or distribute around the domain, we are trying to reconstruct the flow field. So that is what we're trying to do. The size of the network, if I'm not wrong, we are using a very simple, for FLRNet, we are using a very simple one, which is a VGG with 3 convolution blocks, and the number of parameters, if I'm not remember it incorrectly, it is around like 5 million for both encoder, decoders, and the correlations. The volume of the training data, it's quite tricky. We test with, I believe, 20 simulation case, with the Reynolds numbers varying from 200 to 1,000, and each of these simulation cases will be divided into 20 time step, and the time interval in between time step, I believe it is like 0.01 seconds, if I'm not wrong. With the question on the noise, it's actually quite robust. Let me scroll into the result part with the noise in the sensor measurements. So here is on the left side is what we tested on the little noise added in the sensor measurements. What we did was we add a noise Gaussian one. So we don't actually know what is going on with the real sensors. That will be something that we need to address later on. But we try to emulate a Gaussian noise, and with a standard deviation of added noise calculated in meter per seconds, as in here, and then we increase the values of noise. Actually, it's gonna be up to like 10-20% of the original values. And as you can see, the method that we are trying to defend is the FLRNet with Fourier features, and FLRONet, which you will see later on. So as the noise, the range of noise increase, although the MA increase, but it's still like the reconstructed field is still accurate visually, and like quantitatively itself, the MA is within the range that is typically acceptable. Let me see if I can show you some. No, I don't have any of this for this one, but for FLRONet, I believe I do have this. So here is the result on added noise onto the sensors measurements. In the case of FLRONet, so you don't want to see, and like probably you already see the graph, and then the graph is only shows some positive, but the reconstructed field is where you see problem, right? And up to like the noise up to 20%, you still see a robots in the reconstructed field. But I can say that after like 20% of noise added, the model does not perform very well. That is something that we will need to work on more, but we believe that it's also the limitations of the current model. So that's all I can answer for those questions.
Thank you.
Thank you so much. Do we have any other questions for the speaker, Zheng? Yeah. Can you introduce yourself first?
Yeah, sure. Hi, Phong. I'm Zhen Zhang. I'm a postdoc in the Crunch group. It's a nice talk. I have a question about the operator part. Could you please turn to the structure of the Dibyajyoti?
Yeah, please go ahead. Can you say again?
I mean the operator part, Dibyajyoti part. Can you hear me?
Yeah.
Yeah. So yeah, here I noticed you separate the time and the space. I think, yeah, so the time is in the trunk part, and I think the space part is in the branch part, right?
Yeah, exactly.
So can you explain the dimension, for example, of the input and output of the branch and trunk net? Because I think basically we treat all of the coordinates in the trunk, but now I think the spatial coordinates are in the branch net.
Yeah. I see the confusions from your questions. In fact, actually our first initial attempt was to put all of the coordinate part into the trunk net. So we actually have another version of this architectures with like the coordinate is serving the first one. So like we have a branch trunk for the spatial domain first, and then add the trunk part for the temporal one. But at the same time you know that problem, right? Like Dibyajyoti is not the only one, and one of the things that we noticed for Dibyajyoti, it is actually the limitation from our point of view that when you put the coordinate up to the trunk part, it's probably will let you have a more, how to say, like general more accurate mathematical formulations, but engineering wise the training is really expensive. And like it's really that you have to like discretize everything, right? And then record the values for each of these pixel at a certain point at a certain time, and then combine everything into the training data. Versus I myself actually coming from computer vision, so we kind of like prefer something that can do image to image, like if everything can be handled like directly in the spatial domain, we rather will do that. And you know that, right? Like in the spatial domain and the temporal domain, it is not really like that kind of correlation like within the spatial domain itself, right? Like the temporal domain and the spatial domain, they have another type of correlations. And if you can actually handle the spatial domain itself, then it will be much faster. So that's what we find. So it's not really like mathematically it's exactly the same. like the branch net using Fourier neural operators, and the architecture of if you replace that branch net with another branch trunk architecture, where you use the trunk architectures to represent the spatial coordinate, it's absolutely will give you the same result. But the performance and the training wise and the performance when you do the inference, because for this, remember, you need to remember that for this particular reconstruction, we need it to be performed in real time. Like for example, if you put it into a airplane, or if you put it into a submarine, for example, to analyze the fluid flow or the airflow around this, you need the real-time performance. So we need something that going as fast as possible, and then that is where we find Fourier neural operator is very useful, and that is actually the reason for the comparisons between our method and the FNO3D, right? Because you may really ask that, if you can use FNO for spatial domain, why not using it for the temporal domain? And what we have just proved is that you actually cannot do that. It is not like the spatial domain and the temporal domain. It just cannot be the same. So you really need to separate that, and experimentally we find out that if you use the FNO for just spatial domain and the DeepONet for temporal domain, it's work like like a charm. And I actually can refer it to the green function itself. Like for example, if you do a green functions for field-to-field regression, for example, then like if you do time step to time step, it's actually a better formulation. And if you use a green functions for like spatial domain, it is not really efficient as if you use frequency domain representation, like in the case of Fourier neural operators. So it is not really the problem of mathematics, I believe, but it's rather a problem of engineering.
Yeah, so in terms of the prediction or inference, so now I think if we want to query a value at any time, you just put the t in the trunk. But how about the spatial? So I think maybe the output is on a fixed grid of in the spatial domain.
Yeah. So so in the case of the spatial domain, we actually follow the architecture of the Fourier neural operators. So if you really know the Fourier operators, they may convert everything into the frequency domain, right? And they will chop out some of the mode, that is some of the high mode. In our case, we actually do one step further, that we make the mode selections a learnable parameters. So it is more like a adaptive Fourier neural operators. So we let the network that learn which mode to choose to better represent the whole the whole, like the network will choose which mode it is the best, and then you give the best result based off of the data that it sees. Probably with turbulent data, for example, the mode that it choose for the current problem might not be the same, but generally it's kind of like give a relatively good result, and at the same time the speed is relatively fast as well. So that's the engineering selections that based off of our experiment.
Yeah, got it. Thank you.
Okay, do we have any other questions for the speaker?
Can you say again? Sorry.
I think we don't have any more questions, so it's time to move on to our second session. We really appreciated that you stay up so late for this presentation, and thank you so much. Our second speaker today is Dibyajyoti Chakraborty. He will be giving a talk on bin spectral power laws for improved prediction of chaotic systems. Chakraborty is a PhD student at Pennsylvania State University working on deep learning for scientific machine learning, for scientific computing. His work focuses on developing long-term stable AI models for dynamical systems like climate and turbulence modeling. He holds a master's in mechanical engineering from Indian Institute of Technology, Bombay, where he received the Institute Silver Medal, and a bachelor's from National Institute of Technology, Jamshedpur. He has research experience at Los Alamos National Lab, where he worked on forecasting chaotic system as a graduate student intern. With that short introduction, the floor is yours and you can start your presentation.
So hello everyone. So I'm going to talk about bend spectral power loss, and this is the work that I did partly in my summer intern at Los Alamos National Lab. And before going into the details of bend spectral power loss, let me go through the motivation of why we want to do this. So in this project, we are trying to build better forecasting models. So by a forecasting model, I mean that suppose you have the state at time equals to 1 and you want to forecast the state at time equals to 2. So there are two ways to do this forecasting. So the first way is if you have the partial differential equation, you can solve the PD with some numerical PD solvers. And the second way is that you can have an approximation for this solution operator by some neural network. So now the problem of this type of forecasting models comes for chaotic systems when we try to get the long-term forecast. So in this figure, you can see these are forecast from state-of-the-art models. So here the leftmost model is called as FLRNet. This is Pangu weather model, and the rightmost model is GraphCast. So these are state-of-the-art, very big models. But researchers recently, back in 2023, found out that if you try to forecast for long term by using these state-of-the-art models, if you go for forecast at day equals to 30 or day equals to 1000, you can see that either these models became unstable, so they blow up and go to NaN, and if they are not unstable, they start to become non-physical. So you can see in this case that the forecast seems to be very blurry and the model is not very physical anymore. So now this brings us to the question that why this happens. So now this happens because of two challenges. So the first challenge comes from training with mean square losses. So as we all know, we try to optimize these machine learning models with mean squared losses, but researchers back in 1994 had found that optimizing mean square type loss functions on short trajectory does not guarantee the long-term physical behavior. So there have been some solutions for this problem. So the first solution comes from using multiple time steps. So there have been several research papers where they have tried to use multiple time steps into the training, and they got slightly better performance. And when using multiple time steps, they have also found that we need some techniques to compute the gradients properly. So the second solution for this problem that has been there is to use some sort of invariant metric based loss function. So the first metric that people use is some sort of physics information, as they have done in the physics informed loss functions by researchers like Raisi and Lee. Now the second way is to find some sort of distribution based loss function, as they did in this paper, where they used the maximum mean discrepancy loss. Another solution to this problem has been proposed by using hybrid models. So in hybrid models, they try to combine the physics based numerical solvers with the machine learning models, as they have done in this stabilized neural ordinary differential equation back in 2023. And they also use differentiable PD solvers to combine the physics part plus the nonlinear part that is approximated with some neural networks. So now coming to the second challenge. So now the second challenge comes that even if we do these type of regularizations, the problem comes if we start rolling out these models for long time period. So as you can see that if we try to roll out our model for longer period of time, they either become unstable or they start to decay and lose the fine scaled information. So now this second problem is also related to something called a spectral bias in neural networks that had been studied back in 2019. So this spectral bias says that if you want to do a function approximation, as in this plot, they were trying to approximate this function in blue, and they were trying to approximate it using a neural network that is shown in green. So they found out that as you start training the network, so it starts to learn the lower frequencies first, and then it starts to learn the higher frequencies. So this problem is called as the spectral bias in a neural network. So coming into some more details about the spectral bias and its relation to mean squared losses. So suppose, so in this slide, I try to show the training dynamics in the Fourier space. So how does a network train in the Fourier space with the optimization steps? So here first I would like to say that we consider a very general case where f theta is the network and v is the target function that we try to approximate. This f bar and v bar are their respective Fourier series coefficients. So a typical mean squared loss is given by the square difference between these two functions. And we can also define this mean square loss in the Fourier space like this. So now if we consider a continuous version of the gradient descent, and theta is the weights and biases of the network. Now we can say that theta evolves with the optimization step at this. We can say that d theta by d n is minus of the gradient of this loss functions. So now if we try to estimate the training dynamics in the Fourier space, so the training dynamics in the Fourier space is given by d f hat theta k by d n, and we can use the chain rule to expand this derivative in this formula. If we try to substitute these two equations here, then finally this is the expression that we get for the training dynamics in the Fourier space. Now you might see this product term here, and this term is called as the neural tangent kernel in the Fourier space. So let me go further to that. So now the neural tangent kernel captures the first order approximation of a network's training. Mathematically, the neural tangent kernel in the Fourier space is given as this. So in the first paper, the neural tangent kernel was defined in the real space, but in this case, we try to define a similar neural tangent kernel in the Fourier space as well. So, and there are some of the properties of the neural tangent kernels. So the first property is that if we consider an infinite width limit, the neural tangent kernel stays constant while training. It is translation invariant in the real space and diagonal in the Fourier space. And this was shown by Jacob et al. In this paper. So we can approximate the neural tangent kernel as constant in Fourier space, as constant while training, and diagonal in the Fourier space. By this, so now we can put this neural tangent kernel back in this final equation for the training dynamics in Fourier space, and then this is the term that we get finally. So we can say that the training dynamics of a neural network in the Fourier space is directly proportional to some function which depends on the frequency, and then the difference between these two functions. So So now this shows the spectral bias, where the spectral bias is defined as the neural network's tendency to learn the lower frequency components of a target function first and then going to the high frequency components. And there are two reasons why this spectral bias happens. The first reason is because these theta k has larger values for lower frequencies, and this was shown by Rahman et al., where they showed that for ReLU architecture and for certain conditions, they found out that this theta k has larger values at lower frequencies, and also secondly, because these values are larger for lower frequencies, that is also a reason why we have this spectral values, why we have this spectral bias. I also want to focus on this second term. So this second term is related to the gradient of the mean square loss. So the second term is related to the gradient of the mean square loss. And so we can say that because we use this mean square loss, that is also one of the reasons why this spectral bias happens. And in this project, we focus on the second challenge, where we try to mitigate the effect of this second term. So the effect of this first term depends on the architecture, and that is a more difficult problem compared to mitigating the effect of this second term. So there have been some solutions to the spectral bias. The first solution comes from the first paper itself, where they have said that certain architectures have a lower spectral bias, and the simplest of them is to use a larger model. But the challenge with using a larger model comes with the extra cost that we have to consider when we use a larger model. And the second set of researchers have tried to use different architectures that can mitigate the spectral bias. So in this work, they try to use multi-scale hierarchical model, where the architecture tries to focus on different scales separately, and because of that they can mitigate the spectral bias. Researchers have also tried to leverage diffusion models, because diffusion picks from the distribution, and that causes it to not have the problem of the spectral bias. There have also been some very recent work where they have tried to use some different high frequency scaling term in their models. But the challenge with these type of architectures is that we have to define a totally new architectures, and we have to make certain specific modifications in our existing architectures, which may not be feasible for certain applications. So now the third type of solution that is there in literature focuses on penalizing in the Fourier space. So you can imagine these type of loss functions as trying to penalize the mean square loss in the Fourier space, but they also try to weight the different terms in the frequency domain differently. But the challenge with this type of approach is that firstly we do not know the weight that we have to put to different frequency components. And the second challenge is that the amplitudes of low frequency terms the amplitude of the low frequency terms in this type of loss function is very low. It does not make much sense to try to match them in a pointwise manner. So in this research work, we try to solve these two problems. So yeah, going next to the loss function that we have developed. So we call this as the binned spectral power loss. And in this binned spectral power loss, we try to solve these two challenges. So let me start with the second challenge first. So in this second challenge, we try to first find out a function that can define the energy at different scales in a model, and that is captured by something called as energy spectrum. So the energy spectrum is used to define the distribution of energy at different frequency or wave number components. So you can imagine that for a function u, its respective Fourier transform u hat, the energy at different wave numbers is given by half of u hat square. Then isotropic wave number can be defined as k equals to square root of kx square plus ky square. So you can imagine that this isotropic wave number is given by larger and larger larger and larger spheres in this Fourier domain of kx and ky. You can extend it to kz and more dimensions as well. So the energy spectrum is defined by respective binning the energy across different wave numbers. So here we define the energy spectrum by taking binning of the energy in these respective bins. In some experiments, they can also have some weight parameter here. So in our experiments, we use the very simplest binning, which is linear binning, where these circles become larger and larger in a very simple linear manner. So the first it has 0.5, the second is at 1.5, and so on. So now coming to the second challenge that we had is how to adaptively weigh different scales. So, and for this, what we did is that we try to define the bent spectral power loss as this loss function shown here. So here we have 1 minus the energy spectrum of the model divided by the true energy spectrum that comes from the data set. We also have a epsilon, which is a very small positive constant for stability. And we can also multiply this loss function by some weight parameter lambda k that can weight the different wave numbers differently. But in our experiments, we try to keep lambda k as 1. And now, another thing to note here is that because we have this division term, so now you can think that this division term is some sort of adaptive weighting for this numerator term. And because of this, we can give same importance to both lower frequencies and the high frequency components within the model forecast. In practice, we have to note that we also note that since the lower frequency modes in most of our applications were more important, so because of that, we try to choose the BSP loss as the sum of this mean square loss and this BSP loss that we mentioned here. So from now on, the BSP loss that we say is a combination of mean square loss plus this BSP loss term that we show here. And we also have a hyperparameter mu, which is used to keep both these loss terms of the same order of magnitude. So going further, we would like to say that if we do a similar analysis for the BSP loss that we had done previously for the mean square loss, we would like to say that the training dynamics in the Fourier space is directly proportional to theta k, and this term comes from the differentiation of the BSP loss. And here we like to say that the denominator that we have here is the square of the spectrum of the ground truth. This tries to adaptively weigh the Fourier modes that can help in mitigating the spectral bias. So in this, we still note that this theta k term is still present, and that is a different direction of research to try to mitigate this term theta k. But here we try to reduce the spectral bias because of the loss function. So now coming to the computational costs. So here we also say that the major computational cost in the BSP loss comes from the computation of the fast Fourier transform. And the cost of doing a fast Fourier transform is d log d, where d is the dimension of the state, and these are some other loss functions that we try to compare it against. So the first is the standard mean square loss for one time step. The second is the mean square loss for taking t time steps and then back propagating through those t time steps. The third is push forward trick. So third is something called as push forward trick, which was shown in this paper. So this push forward trick is very similar to the mean square loss in t time steps, but here we try to detach the gradient after every step. This maximum mean discrepancy loss was proposed by researchers called as SCIF. This was proposed last year. So I believe this is a team from Google Research. So they proposed this maximum mean discrepancy loss. We'll not go into the details of these loss functions because of the time, but I want to say here that the cost of computing BSP loss is lower than the cost of computing maximum mean discrepancy loss, or the cost of doing a mean square loss for multiple time steps. So here the extra cost that we have is log of d, and log of d is not that large because d is the dimension of the state, and you can see that log of d may not be that large compared to some of these other terms. So now coming to some of the applications that we did. So for the first application, we tried on the same problem that was shown by Rahman et al. In their spectral bias paper. So here the function that we try to approximate is a made-up synthetic function where we have different set of frequencies k1, k2, and their respective amplitudes, and we use random phases to make this synthetic function. And here we try to compute. So here the first row of images is for the BSP loss, and the second row of images is where we try to learn the same function with a mean square loss. And you can see that in the beginning of the optimization, both of them do somewhat similar, but if you do more and more optimizations, you can see that the BSP loss does really well to capture most of this frequency amplitude. In the other case, the mean square loss does not do as good compared to the BSP loss in capturing these amplitudes. So now coming to some more realistic problems. So the second problem that we see is for a 2D homogeneous isotropic turbulence case. So this is a data set at Reynolds number 1000, and the DNS data set is taken from this paper. And the DNS was actually computed on 2048 square. We downscaled it from 2048 square to 64 square because of computational resources. And the baseline model that we used is dilated CNN. So a dilated CNN is very similar to a standard CNN. The only difference is that the kernels in a dilated CNN, they have gaps in between, so it can see a larger receptive field. And the baseline models that we compare against are the neural ordinary differential equation that we call as node in this case, and this multi-step penalty node. This multi-step penalty node is just a better version of the standard node, and we also compare it against the maximum mean discrepancy loss. So these are all the same model trained with these techniques. So now in this image, this first row for the dilated CNN, so the first row is for a standard mean square loss trained dilated CNN, and you can see that in the beginning of the forecast, in the beginning of the forecasting task, you can see that the model does really well. So here the bottom row is the ground truth, and you can see that in the beginning the model does really well, but after a certain number of time steps, the model starts to diverge from the ground truth and become NaN. So I would also like to say that both this node and MP node, these models are stable, but you can see that their predictions become blurry after a certain number of time steps. Would also like to say that the model trained with maximum mean discrepancy loss does somewhat okay in the shorter time scales, but as we go to larger time scale when this starts to become nan. And then finally, the model trained with the BSP laws does really well, both in the shorter time scales and the larger time scales. You can see that for the shorter time scales, the model can match the ground truth exactly. In the larger time scales, the model does not match the ground truth because it is a chaotic system, and because of the chaotic nature of the system, the model deviates from the ground truth. But still, at least visually, you can see that the model looks stable and reasonable enough. So coming next to some more plots. So in this slide, we try to plot the spectrum and the correlation with DNS. So the first plot is the spectrum compared with the DNS data set. So here the y-axis is the value of the energy spectrum, and the x-axis is the wave numbers. So you can see, and the ground truth data spectrum is given by black, and the model trained with BSP loss is given with this dashed line. So you can see that the BSP loss can match the spectrum of this data set really well compared to other models. So most of these models either have a decaying spectrum. So the models that are stable, they have a decaying spectrum. So you can see that these two are node and MP node. So these two have a decaying spectrum, and the model which are unstable, they have a spectrum which is not decaying but starts to go larger and larger. So another plot is the correlation comparison with DNS. So in this plot, we would like to say that the BSP loss does similar to the standard model, which has been trained with the mean square loss. So we also mention that it does not improve the correlation with DNS, but the correlation with DNS is nearly the same as the model with mean square loss. So as compared to this, the model trained with the maximum mean discrepancy loss matches the correlation with DNS really well. So you can see that the model trained with maximum mean discrepancy loss does better. And this was stated by their paper as well. So we would like to say that this binned spectral power loss is more useful when we want to see the long-term trend and not just the short-term correlation. So some more plots in this slide. So in this slide, we try to plot some invariant metrics of the flow. So here the plot on the top left is the distribution of the pixel-wise vorticity. On the top right is the distribution of the pixel-wise velocity. On the bottom is the distribution of the turbulent kinetic energy, and on the bottom right is the distribution of the dissipation rate. So there are so many plots in this image, but the main thing which I want to show is that the ground truth distributions in all these plots is given in this black lines, and you can see that the distribution of the model trained with BSP loss is given by this dashed blue line. So in all these plots, you can see that the dashed blue line is the most close to the ground truth distribution, which is given by the black lines. So coming to some other plots, some other experiments where we try to compare this BSP loss with some previously done FFT-based regularization. So the first loss term where researchers have tried to do regularization in the Fourier space was called as Sobolev loss. So in Sobolev loss, they just have a different weight. So here the weight is given by 1 plus the wave number square, and this weight is multiplied to some sort of mean square loss in the Fourier space. And then we also try to compare it with a relative FFT loss. So in this relative FFT loss, the loss function is given as this. And we would also like to say that this loss is very similar to BSP loss. The only difference is that here we do not do any binning. So in BSP loss, we have binning, but in this case, we do not do any binning. So yeah, And the plot that we show here is called as the total variance distance. So in total variance distance, we try to show the difference between two distribution. And in this plot, we show the TV distance between the predicted and the two Fourier spectra. So this plot is defined in the Fourier space where we have kx and ky. So here, I think kx should be this one and ky is this one. And in this case, we can see that the darker values means lower value. The darker values means lower TV distance, and we can say that the BSP loss shows the lowest total variation compared to these other models. We also have to note that the Sobolev loss does really well as well, but the BSP loss still does the best in this case. Coming to some other applications, so in this we try to do more challenging, we try to apply it on a more challenging data set where we have a 3D homogeneous isotropic turbulence, and the DNS is taken from this paper by Mohan. And the baseline model that we use here is called as the 3D UNet model. This model is a much larger model compared to the previous models, and we found out that a larger model has lower spectral bias. So in this plot, you can see that we have the model predictions. So here the left one is the BSP loss, the middle one is the mean square loss, and the right one is the DNS. So in this plot, visually, we can see that slightly the BSP loss has more detailed information compared to just using the mean square loss. We can see visually here that this middle plot looks slightly blurred compared to these two plots. And that is more evident when we try to see the spectra. So here we can see that the DNS spectra is given in blue, and the BSP loss can match the model trained with the BSP loss can match the spectra really well for most of the time steps. And we can also see similar behavior in the QR plots. So the QR plot is a comparison of the first and second. It's actually distribution of the first and second order metrics for turbulence. And we can see here that the BSP loss does slightly better compared to the mean square loss. So now coming to our final experiment. So our final experiment is actually related to a problem where the BSP loss did not do that well compared to the previous experiment. So here, and the reason for this is that BSP loss is non-trivial to compute on a unstructured mesh. So in this problem, we have flow over the wings, and this data set is taken from the Deep Blue repository, which is a turbulent wake flow downstream of a NACA airfoil operating at a NOS number 20,000. But the main challenge in this data set is that this data set is point-wise and not structured, and because of that, we try to convert it to a rectangular mesh first. So it was done by previous researchers. But the challenge here is that the spectra of the baseline model looks very similar to the spectra of the ground truth. And because of that, the BSP loss is not able to improve it further. But still, we can see, if we look really close, we can see there is more details in the simulation, in the forecast of the BSP loss compared to the forecast of the model, which is just trained with mean square loss. But the challenge here is that the spectra of the model with just mean square loss is also really good compared to the ground truth, and because of that, the improvement we see here is very minimal. And we also try to compute the distribution of the values at this red point that we see here, and we can see that the distribution of the model trained with BSP loss is much better compared to if we do not use the BSP loss here. This red distribution is for a CVIT model. So CVIT model is a much larger continuous vision transformer model, and we can see that the distribution of the BSP loss is more or less similar to a much larger model as well. So these are the conclusions of my research. So the first conclusion is that the BSP loss focuses on the spatial energy distribution that can help us to model both larger scale structures and fine gauge and fine structures in the model, and we can get significant performance gain without modifying the neural network architecture, and the computational cost of computing a BSP loss is also lower, and we have demonstrated the effectiveness on several challenging test cases, and some of the future works in the BSP loss might be to extend it to some non-structured mesh. So yeah, that is pretty much from my presentations. So,
Thank you
yeah,
so
feel free
much
to ask questions.
for
Yeah.
your great presentation. Yeah.
Yes.
Vivek, can you introduce yourself first and
Yeah.
then?
Hi, my name is Vivek, and I'm a PhD student working with Professor George Karniadakis.
Yeah, Vivek.
Thank you, Dibyajyoti, for the amazing talk and really cool results.
Yeah,
I have a
thanks.
few questions. First, regarding the choice of mu, you said the mu was chosen so that both the MSC and the actual BSP loss has the same magnitude. So
Yes.
you do like a warm-up run, see their magnitudes for a few
Yes, exactly.
and then
Yeah.
decide and went ahead. So
Yeah.
typically, what is your mu in that case?
So I think it depends on problem to problem. So if I remember correctly, my 2D turbulent case, this mu was just one because these loss value had typically similar magnitude. But I think in the 3D turbulence case, this mu was larger because this BSP loss was lower because the model was bigger and the spectra was
Slower.
good by default. So this mu was larger. Yeah, but I think it depends on problem to problem.
Problem. Yeah, I agree. I understand. Yeah. I have another question about the 3D turbulence case.
Yes, sure.
So, let's say the intermittency plots you are plotting in the next slide.
Yes.
So this, okay, this is the energy spectrum. Okay, so how far did you try forecasting, and in terms of the eddy turnover times?
So here the one cycle of the turbulence was related to 30 time steps.
Right.
We forecasted for 30 time steps. So you can see here that the time
Right.
step is 30. And the reason why we did not go beyond is because the total training data set that we had nearly 300 time steps. So we could not go.
I
So,
understand.
yeah. Yeah. So one cycle of turbulence here is nearly about 30 time steps.
Yes, so you are
Yeah.
trying to forecast like one cycle up
Yes.
in this plot, and in the earlier, like you said in the previous slide, when you show there are like fifth autoregressive rollout, that is corresponding to 5/30th of a cycle, right?
Yes, yes. So fifth autoregressive rollout is like 6/30.
Yeah, right.
Yeah.
6/30th of one so
Of
the
one
cycle,
cycle.
yeah, one
Of one
cycle,
cycle. Yeah.
which is the eddy turnover time.
Yes, right. Right.
Right. And just one last question for
Yeah,
this
sure.
problem. What is the flatness of this homogeneous isotropic turbulence data set?
I think for the flatness, did not go into the details of the data set as such, but I think if you read this paper by Mohan et al., you will find more details on this. Yeah.
I'll do that.
Yeah.
So thank you. It's a great talk and really cool results.
Yeah.
Thank you for your time.
Yeah.
Thank you so much. Do we have any other questions for the speaker?
I have
Yes,
one
Siraj.
question. Yeah. Hi,
Yeah,
Can you
sure.
introduce yourself first? Yeah.
Yes. So I'm Siavash. I'm currently a postdoc in Brown working with George. So we've been also working on spectral bias mitigation for like chaotic systems such as turbulence in 2D and 3D. So one observation we had so far is that if you start manipulating the MSC loss,
Yes.
you can probably get a better energy spectra alignment, which is cool. But so you can mitigate the spectral bias, but the actual average error increases. So I'm wondering if you have also observed.
Yeah, I think you are right. Let
the same
me
thing.
show actually. So in this plot, you can see that. So if you try to make the model have a better spectra, then somewhat you can see that the short-term correlation with DNS is slightly lower. I mean, not as much, but you can see that the short-term forecast accuracy decreases slightly. So yeah, that is a trade-off that we have to make, and that can be somewhat done by adjusting this mu.
Mhm.
So if you want to have a better mean square or a better short-term forecast, then you can have a lower value for this mu. So I guess, yeah.
Okay, got it.
Yeah.
Yeah, thank you so much. It was a really nice talk.
Yeah, thank you so much for having me here. Yeah.
Thank you. Do we have any other questions for the speaker? I think there is no more questions. So thank you so much for being here and joining us today to give the talk. And yeah, thank you everybody for joining us today. I hope everybody has a great weekend ahead. And it's time to close the
Of course, yeah.
session.
Thank you so much. Yeah.